Hello and welcome back to EGR 171 Fluid Systems. In this one, we're going to be looking at conditioning system fluid. This goes along with chapter 12 in your textbook. And when we talk about conditioning, it's essentially how do we maintain the various properties we want our fluid to have? Things like viscosity, cleanliness, temperature, etc. So we'll be looking at the devices and systems involved that maintain those fluid properties.
While fluid conditioning may not seem as important as some of the other functions of a system, for long-term cost effectiveness, it's essential. It has a lot to do with how well your system works. It has a lot, well, how reliable your system is and how long it's going to function. So this conditioning systems are very important. Essentially what we're trying to get them to do is make sure they maintain the fluid at the right level of cleanliness, and keeping contamination out of it, and your acceptable operating temperature, making sure it doesn't get too cold, too hot, etc. It turns out that studies have shown that about 75% of all the failures in hydraulic systems are actually directly related to contamination. While they may not fail from contamination right away, oftentimes the long-term effects of contamination build up and eventually cause failure. So all things considered, it's very important to do this, and it will definitely have a long-term benefit and cost benefit as well. It's important to understand where contaminants come from. If we understand their source, we can potentially work to prevent them or at the very least correct them. Turns out when we talk about contaminants, we're primarily talking about solids or liquids. When I talk about solids, we're talking about relatively small particles. The key thing is that essentially anything that should not be in the system itself. Now, one major source that people often overlook is during the initial manufacture. When components are shipped, they could potentially get contaminated. Packing material, fasteners, etc., are all things that potentially could be built get into the system during the actual construction. There's a whole process for cleaning out systems after manufacturing occurs, but that potentially could be where we get at least our initial sources. Now, they can enter the system from the outside environment during normal operation. For example, see construction equipment over here on the right. Obviously, it's exposed to dirt and gravel. Particularly the hydraulic cylinders extend out into that environment and retract back. They could certainly be bringing in contaminants. Another area where contamination occurs is as components wear. As that material breaks down, that can potentially get in the system. This could be worn metal fibers, also could be seals breaking down, or even the fluid itself. Keep in mind, as fluid oxidizes, potentially forms sludges and varnishes, which are other forms of contamination. The reality is, even if you avoid all of these, during normal operation, there's a certain level of contamination that's going to occur. The fact is, we have metal-to-metal contact that wears. Seals do break down over time. So regardless of how careful you are, you do need to have a relatively robust filtration system to remove these contaminants. So we're going to talk about prevention. We're also going to be talking about removal. So why is it so important? Well, as I said, about 75% of all failures are attached to it. But why, I guess, do those failures occur? Keep in mind what contamination does in hydraulic fluid is it reduces the fluid's ability to do a number of key things. For example, provide lubrication. If you look over here on the right side, you see what I believe is the housing for an external gear type pump. You can see this wear surface. You can see the material being worn away. That is very likely due to the fact that the fluid itself was contaminated in some way, or materials got in there that was contaminated in some way that prevented that lubrication from occurring. Keep in mind, as they wear, the seals break down, and those clearances will potentially get larger that allow more leakage. Contaminated fluid is not nearly as effective in transferring heat and energy. And then, of course, the wear and functional parts eventually cause problems in the functioning of your circuit itself. Right? The Leakage is going to reduce efficiency. It could reduce how much force you could put out. It could definitely slow your, if there's a lot of leakage, you could slow the motion of your actuators, for example. So these are all things that contamination can potentially do to your system. One of the major things we want to maintain is the operating temperature. Fact is, hydraulic fluid is designed to work in a relatively small window, and as a result, we want to make sure that the fluid never gets too much beyond that window, or it will affect the overall operation of your hydraulic system. Keep in mind, hydraulic systems do generate a decent amount of heat. If you're around hydraulic equipment or for any mechanical equipment, you'll find that it's going to warm up. That heat that you're feeling is coming from the energy of the system. And even very efficient systems end up converting about 20% of their power input to heat. That's not necessarily means that it's only, say, 80% efficient. Overall, it's 80% efficient. But keep in mind, there's usually a lot of downtime in hydraulic systems where they just operate, not necessarily moving anything at that time. And during that point in time, essentially all the energy is going to be converted over to heat. Now, we usually check this at the reservoir. So a reservoir is where our fluid is going to sit, and we're generally going to be checking the temperature there. You can check temperature in other locations, but keep in mind you don't have a large pool of fluid. Only in the reservoir is there a large quantity of fluid to measure the temperature. And what we're usually looking for is a range between 110 and 140 degrees. And this is for hydraulic oil, keep in mind. Obviously, if you're using a different hydraulic fluid, say something like a fire-resistant fluid, it would have a different temperature range. So what happens if you get outside of that operating temperature range? Let's say, for example, your oil gets too hot. Well, two things that can potentially happen. One, your oil itself can start to break down. The fact is oil oxidizes at a certain rate regardless, and the hotter it gets, the faster it oxidizes. That can lead to things like sludges and varnishes in your system. The other thing about it is that hot oil is not particularly viscous, right? It gets to be very thin, and as a result, it's not nearly as good a lubricant. It doesn't provide as good seals, so your leakage rate, your wear rate could go up. On the flip side, if your hydraulic oil is too cold, right? Say, for example, we're seeing here a piece of construction equipment operating outdoors in the wintertime. Well, then the oil is going to be too viscous. It's going to be too thick. That's going to not flow particularly well. And as a result, it's going to be difficult to get the fluid to flow into the pump. It's going to be that much harder to push it through the pump. And what you're going to see that in is significantly higher pressure drops, right? And the overall operation of the system is going to be slowed down because not as much fluid is going to be moved around. Also, keep in mind, long term, that's problematic. That's going to generate a lot of inefficiencies and potentially cause additional wear because you're going to have to put additional torque into, say, the pump, etc., and potentially have issues with filtration. So the list goes on and on. There is many good reasons why you want to make sure your hydraulic fluid operates well within that temperature range. Now, keep in mind, it's a balance because your system itself is generating heat, and your various components, particularly your reservoir, is conducting heat out of the system. System also is radiating heat directly, and if there's any kind of air movement around, you might have convection. And so you want to get it to that temperature, but then you want to keep it at that temperature by keeping the balance of heat generation and heat removed essentially at equal, so there's no net change. We're also going to try to maintain a level of contaminants. As I said, you're never going to completely remove contaminants, but if you understand the sources and you know how they're entering the system, one, you can avoid them. If it turns out, though, that contamination does start to build up, this is something you really need to report, and you really need to come up with a solution. Keep in mind, there's all the negative effects of contamination that we want to avoid. So once you find that you're getting a high level of contamination, you need to go back and find it. Right? This may mean servicing the equipment. It may mean changing the filtration system. It may mean changing something about the environment at which the system is operating in. While you may not think of this initially, your reservoir is actually very effective in controlling contamination in your system. Um, the whole idea behind your reservoir is to store fluid, but keep in mind it's also designed to provide a essentially place for the fluid to rest. During that, we want to make sure that any type of contamination separates out from the fluid. So most solid contamination we're hoping is going to drop to the bottom, and any type of gas contamination and trapped air, etc., is going to rise from the top. Reservoirs are designed with a sloped or dish-shaped bottom with the idea of those solid contaminants going to one location, and then when you drain off the fluid, the contamination is relatively easy to be removed. If a major amount of contamination, however, just draining it out isn't necessarily going to be effective, and you'll see on nearly all reservoirs we have some sort of clean-out plate on the side, or perhaps the top is removable for you to actually go through and clean it out in a complete manner. That, of course, requires you to remove all the fluid, but in certain situations, if you have a lot of contamination, it's necessary. In addition, we're going to have strainers and filters that sole purpose is to trap contamination, right? Essentially, any material that won't break down as insoluble will be trapped in one of these physical filters. Generally, they're broken into two categories. Strainers tend to be relatively coarse filtration, essentially devices with small holes in them where those particles can't go through those holes. Right? They're usually relatively thin material, but and not designed to hold a lot of contamination, but to prevent any type of large particles from getting through for physical objects. Filters, on the other hand, are in a number of different forms, but they're usually designed to do fine filtration. Right, so they're trying to stop small particles from getting through. You could come up with some sort of very fine mesh for this, but keep in mind that potentially is problematic because that's going to cause a lot of pressure drop. Right, so you're always going to have to balance the amount of filtration versus the cost in terms of pressure and efficiency of your system, because there is a cost associated with this. Because you're going to have to force the fluid through a strainer or a filter. So all the various devices that are going to be associated with cleaning our fluid falls in the categories of strainers and filters. If you look here on the right, you can see an example of how they appear. You're actually not seeing the filter itself. This is actually the housing. Fluid would come in this port, oftentimes out the other side, and some or all of the fluid would be put through a filter that is hanging below here. Again, these are usually mounted vertically with the filter itself hanging below, with, again, the idea of the contaminants, usually heavy contamination, tends to drop towards the bottom. They're going to be constructed of a porous material, right? Since porous essentially filled with holes, and that's going to try to prevent or trap the insoluble materials. So any solid materials that won't break down. They're going to be rated for a certain size. So essentially any contaminant that's going to be larger than that should get trapped. And the idea is for them to last for as long as possible. Filters can be expensive. Shutting down the system is problematic. It can be problematic. So you want them to have a certain service life. And that's something you're going to build into your preventative maintenance schedule. They are designed to be serviced relatively easily. Oftentimes you'll see these covers are designed to just screw right off. You can then replace the filter itself and put it back together and get your system back up and operating in only a few minutes. So there are variations on that, but that's the common mechanism for mounting filters and systems. There's also some other devices you'll actually see on the tops of here that will talk a little bit about indicators, valves, etc., maybe a pressure gauge as well, that are all kind of integral to the system. So in terms of the material, we have a number of different forms. The simplest one, and one you've probably experienced if you ever worked in a pool or worked with your oil filters in your car or whatnot, is a surface type filter. Right? This is a filter that has a corrugated surface. right? And the whole idea of this corrugated or accordion surface is to maximize the amount of surface within the package size. And it's considered a surface type filter because the filter is going to be trapped right at the surface. We're trying to maximize the size of it so it can hold as much material as possible. Because keep in mind, one thing that's problematic about surface type filters is once those holes, those passageways start to fill up, then you're going to tend to have a clogged filter and cause pressure drop. So these are inexpensive, but one of the downsides of them is they don't have a very large holding capacity. But they're relatively inexpensive. These can be made with wire mesh or molded cellulose, essentially just paper, and in most cases they're designed to be disposable. Wired mesh ones, on the other hand, I should say that they're usually designed to actually be cleaned. Another method for doing this is using a depth type filter. Depth type filter essentially looks something like this. It's a mat of material, relatively random, and it's a chunk, essentially, a solid volume of material. The whole idea of it is the fluid has to pass through it. To pass through this, it's a relatively tortuous path, and small particles will get trapped, in part because the holes are so small, but also in part because they just get stuck on these various surfaces here. They can be made of a variety of material, but the most common is cotton and wood pulp. And the whole mechanism of this is to essentially trap it and hold it. We can also use other types of filters like these to remove chemicals, right? If we use, for example, things like charcoal and things like that can actually absorb chemical materials as well. So both of these are designed to kind of hold things in throughout the depth of the filter and to react with it if it's a chemical treatment as well. In terms of the level of filtration, different filters will be rated at different sizes. Essentially, what they're going to tell you is how small the particle can be that will be removed, or anything smaller than that is going to pass through. These are usually measured in microns, and keep in mind, a micron is a very, very small size. It's less than a 10,000th of an inch, about half a 10,000th of an inch. In general, the filtration on hydraulic systems, we want to have a filtration level of 25 microns or less. But that, of course, depends on the system, and some systems are actually designed to handle higher levels of contamination. We'll see a couple of different ratings. Generally, we're going to see what's referred to as the absolute rating and the nominal rating. This is kind of problematic that we have two different ratings. Absolute rating will state what your largest pore opening is. So it pretty much guarantees that anything bigger than that is going to get stuck. On the other hand, nominal rating, which a lot of filtration companies use, will actually tell you what the average size it's going to trap. And this tends to be the case when we're dealing versus nominal versus surface types. It's pretty easy with a surface type filter to come up with an absolute rating because you know how big the holes are. But when you're looking at a depth type where that random oriented mesh, you really are looking at it more of a statistical probability that a certain amount of material is going to get trapped. As someone working in hydraulic systems, it's important to understand the difference between these absolute and nominal filtration ratings. Keep in mind, if you are looking at nominal ratings, again, that there is the potential for larger contaminants to get through. If this is a major problem with your system, you want to make sure that you alter your filtration system. Keep in mind, just like all the other components we have worked with, it's important to look at all the details provided by the manufacturers. They have data sheets just like they have with other equipment, and you want to make sure you pick a filter that meets your needs. So definitely know the difference between absolute and nominal filtration rating, and of course consult with your data sheets when selecting a filter. I should also point out that for most hydraulic systems, they have more than one filter in their system. So pretty much all of them will have a strainer and a separate filter, and they may have even more than that. Generally, when we see a filter in a hydraulic system, we're actually seeing the filter housing. For example, there's one shown right here. There's a number of different styles for these, and we can place them in different locations depending on how we want them to function and what we want them to do for our system. One of the features that's common to a filter housing is it has a built-in or integral bypass valve. And in case the filter ever gets so clogged or so dirty, we want it to be able to bypass it. If not, it's going to either prevent fluid from flowing or cause a pretty major pressure drop. So they're going to be built in. And at that point, then, though, the filter stops working. So we need some way of telling that. And we can see, for example, in here and down below, we can see a pressure indicator. And essentially, it tells us as the pressure goes up, this is it functioning well. It's going to go through this area here, white or yellow, meaning it's getting close to its service life. And once it reaches red, we want to be able to take replace that filter or clean that filter. In addition, we can have indicators that are digital in nature, so they go back to some sort of monitoring equipment to say, oh, time to change that pressure system as well. So it doesn't necessarily always have to be a physical one. It's also important to consider in terms of its location if the filter housing is going to work well. Is it made of the right materials? So for example, if you're in an external case, you might need a metal housing to make sure any type of, like, say, rocks or any type of debris might hit it. Temperatures might prevent you from using a plastic housing, etc. So you want to make sure that it survives well and works particularly well. You'll also notice in terms of the actual setup, generally these are mounted vertically with the filter hanging below. Turns out we can locate our filters in usually 3 different locations in our circuit. And it's important to differentiate these because depending upon where they're located, we're going to get different functioning for the filtration portion of their service, but it's also going to affect the overall function of the circuit as well. So those 3 locations are at the pump inlet line, so essentially where the fluid's sucked in a system working line, or in a return line, essentially going back to the reservoir. So let's look at each of those separately. So at the inlet line, we're generally going to have a strainer. This is referred to as a sump strainer, and it's usually attached right to the end of the inlet line, and it's going to be submerged in the hydraulic oil. The whole idea of the strainer is to protect our system from any large contaminants. This could be dirt that's in there. This could be any type of large metal wear, say a metal file or something like that. That all can potentially get into our system. We want to make sure that stays in the reservoir. Hopefully the idea is it stays in the reservoir and eventually drops to the bottom and we can clean it out. We can also put a suction filter in there. A filter, as I said, is going to be finer for finer contaminants, and this could be on the suction line, but it's not going to be submerged in the fluid, so it'll be outside the reservoir. Keep in mind, we want it outside the reservoir so we can easily clean it and do any kind of servicing. Generally with strainers, you don't have to worry about it. They are simple devices, and unless you're getting a lot of contamination in your system, you're not going to clean it except for when you clean the reservoir in general. Now, there is one problem with putting filter on the suction line, and that is that it has the potential to cause pressure drops. And when we're trying to pull fluid into our pump, as you can see here, we have our filter right in line, it's being pulled into the pump. If you cause significant pressure drops, that can lead to cavitation issues in the pump itself. So while it's a possible location, it does have potential problems, and unless you have some way of designing around it, generally small-scale filters will are not common on the inlet side. Some strainers, on the other hand, are very common, and pretty much all industrial hydraulic system has this strainer built right into it, submerged in the inlet line. We can also put it right in a system working line. So in this case here, we have the fluid coming out of the reservoir, it goes into our pump, and all of the fluid is going to go through our filter before it goes out to our valves into our system. This case here, this works pretty nicely. It definitely is going to protect our downstream components from any level of contamination. But the negative effect of this is that it does have that whole issue with pressure drop. And this location right here is going to be our point of maximum pressure. Right, this is before any of the pressure drops caused by the system. So our filter has to be a pretty robust filtration device, and it needs to be able to function well in there. So this is a better feature, a better location than our suction line in some cases, but it's not necessarily the best. Now, what it does do, however, is particularly if you have a very high precision system and you want to make sure that no contaminations get into it, this is a great location for putting your filter because it prevents any of those contaminations from getting any further down. By far the most common place to put a filter is on the return line. If you take a look here at our circuit, come from the pump through our valves, in this case to a linear actuator, and on the return line going back to the reservoir is our filter. This is going to be usually connected directly to our control valve, our directional control valve, and be between that and the reservoir itself. Obviously, the rate of fluid is going to depend on what's going on in your system, but keep in mind all the fluid that's going through the circuit will eventually have to go back through this filter. This does have other issues with back pressure. Fact is, if this causes a significant prevention in here, if this acts as a block in here, it's going to build pressure up all the way back through the system. But it tends to be at a much lower pressure. It tends to be near your reservoir itself, which is something you're going to service. And if you have a large enough reservoir and you keep it clean, you shouldn't have any problems with pressure buildup. In addition, we're going to have some choices of how the fluid goes through filtration and how much of the fluid goes through filtration. Pretty much everything we've described so far has been a full flow filtration system, where essentially all the fluid going through the system is going to go through the filter. But that's not always cost effective, in part, especially if you're going to go for a very fine filtration system. In those cases, that's going to cause a pretty major pressure drop in the system, and if you were to put it in the main line, that could be problematic. In those cases, we would use what's referred to as a proportional filtration system. In that case, some of the fluid goes to the filter, and usually it's a separate portion of the circuit itself. The idea is that eventually all the fluid is going to go through it, but it wouldn't all go through in every time it circulates. Another option, particularly if you have a large amount of contaminants, is to use an offline filtration system like the one shown here on the left. This would be something you'd connect up to your system, may run, say, at night or on a regular schedule, and it has large filters on it, its own separate pump and motor, and essentially it has a much larger contaminate holding capacity. Some of you may have experienced this if you ever worked in the fast food industry. They use a similar system to actually filter the hot oil in a fryolator to eventually clean out all the contaminants. So it's not just necessarily something from the hydraulics industry. So as I said earlier, filtration is critical to the overall maintenance of your system. And to do this, we're going to develop a routine maintenance plan in most industrial environments. Things that need to be done on a regular basis is the filter needs to be replaced and the hydraulic fluid. Keep in mind that breaks down. When you're doing that, you're often going to clean the reservoir. You will have solid contaminants at the bottom, water at the bottom, etc. But other things that should be built into your schedule and your processes is to make sure that when the fluid is not in the system, when it's being stored, that it's stored in a clean area in sealed containers. And when you're actually doing the filling, that you're using clean containers, hoses, and of course funnels. They are also potential sources of contaminants. So make sure those are all clean as you're putting them together. The thing about it is filters themselves, while you're taking them out, you want to handle them very carefully because you want to make sure that all that contaminant that are trapped in there don't end up separating and falling into the system. So you want to remove them very carefully to avoid any additional contamination.